Plane wave propagation. Hi everyone. I am Saranga Bandara from the Open University of Sri Lanka.
Introduction to electromagnetic waves. Electromagnetic or EM waves are generated by time-varying electric and magnetic fields that are mutually perpendicular and propagate through space. The existence of EM waves is predicted by Maxwell's equations, which unify electricity and magnetism. The wave equations for both electric and magnetic fields are derived from these equations. EM waves can propagate through free space, dielectrics, or conducting media, depending on the material properties. The energy carried by an EM wave travels in the direction given by the pointing vector. Examples of EM waves include radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays, all differing only in frequency or wavelength. Wave equation derivation. We start the derivation from Maxwell's equations in free space. We can list the derivation steps as follows. First, we take the curl of Faraday's law. Then substitute Ampere's law into the right-hand side of the equation. The next step is applying the vector identity and consider the free space. Similarly, this process is applied to the magnetic field too. Then these are the vector wave equations for the E and H fields. They describe how electromagnetic waves propagate in free space at the speed of light.
Definition of plane wave. A plane electromagnetic wave is a special solution of Maxwell's equations, in which the electric and magnetic field vectors vary only along one spatial direction. The phase of the wave is constant over infinite parallel planes, hence the term plane wave. Physical meaning of the plane wave is: each point on a plane perpendicular to the z-axis experiences the same field magnitude and phase. Therefore, these planes are called planes of constant phase. The wavefronts move in the direction of the propagation vector, propagation constant, and phase velocity. Propagation constant, beta, represents the rate of change of phase with distance. It determines how fast the phase of the wave varies in space. The phase velocity, Vp, is the speed at which a point of constant phase in free space, it is equal to the speed of light. These beta and Vp are medium-dependent parameters, and for a lossy medium, beta becomes complex. It will introduce attenuation. Field relationships. For a uniform plane wave, E, H, and K are mutually perpendicular. Magnitude relation is related to intrinsic impedance, as in the equations. Wave polarization. Polarization describes the orientation and trajectory of the electric field vector as the wave propagates through space. Since the electric field defines the wave's orientation, polarization is always described in terms of E. Linear polarization. The electric field maintains a constant direction and varies only in magnitude. Occurs when two orthogonal components of are in phase or 180 out of phase. The tip of each race is a straight line. Circular polarization. The electric field has two equal orthogonal components with a 90-degree phase difference. The tip of each race is a circle as the wave propagates. Can be right-hand or left-hand circular, depending on the rotation sense. Elliptical polarization. The most general form of polarization occurs when orthogonal components are unequal in amplitude or not exactly 90 degrees out of phase. The tip of describes an ellipse. Plane wave in lossy medium. In a conducting or lossy medium, part of the electromagnetic wave's energy is dissipated as heat due to the material's finite conductivity sigma. Maxwell's equations must include conduction current density, J. The propagation constant, gamma, can be written as a combination of the attenuation constant, alpha, and the phase constant, beta. In lossy media, waves experience both phase shift and attenuation. power flow, and pointing vector. Electromagnetic waves carry energy as they propagate. The rate of energy transfer per unit area is represented by the pointing vector. The direction of the pointing vector gives the direction of wave propagation and power flow. Instantaneous pointing vector, ST equals ET into HT. Time average power density for sinusoidal waves gives the average rate of energy flow over one full cycle. It is commonly called the complex pointing vector. The physical meaning of the pointing vector is the average power per unit area. The direction of power corresponds to the wave propagation direction.